Today we'd like to talk about the connection between wavelength and frequency for light of low frequency. So I want to remind you, first of all, that frequency is generally determined by the source of the wave. The velocity is determined by the material that the wave is traveling through. And wavelength is determined by both. Wavelength depends on the velocity of the material and the frequency of the source. Okay, I want to make sure you remember that light has different frequencies and they correspond to different colors. So when we think about light and we think of the spectrum, Roy G. Biv, each color has its own unique range of frequencies that will produce that color. I want you to realize that not all of the frequencies are visible to the human eye. In fact, it's just a small slice of frequencies that we can actually see. So we're going to go through a brief overview of each of the different types. We're going to start today with just the low frequencies, the radio, the microwave, and the infrared. So radio waves are the lowest of all frequency lights. Remember that radio waves, just like other light waves, are started by an oscillating or accelerating charge, usually an electron. They oscillate them back and forth inside of a antenna, and they produce a series of waves in the electromagnetic field. Each radio station will have its own unique frequency that it oscillates the electrons. If you're listening to an FM station, that will be oscillating them very quickly. They will be measured in megahertz. So if you're tuned to 96.6 FM, that is 96.6 megahertz. 96 million cycles, oscillations per second. If you're listening to AM, they're going to be designated in kilohertz. So if you are listening to, let's say, 900 kilohertz AM, that's 900,000 oscillations per second. Realize that the radio spectrum is much larger than just AM and FM, and the government has designated different frequencies for different purposes. It's incredibly complex. However, you can simplify it down to the big categories that generally fall in certain ranges. So the ranges are very low frequency, medium frequency, high frequency, very high frequency, ultra high frequency, super high frequency, and extremely high frequency. So we've got all of these different sections of the radio spectrum. And you can see how FM falls in one range, Wi-Fi falls in another, and AM radio falls in another. So we have different areas of the radio spectrum saved for different types of radio transmissions. When we talk about encoding a signal on a radio signal, we do something like this. The carrier is the actual frequency that you would tune to. So if we were at 96.6 FM, that would be 96.6 megahertz. And that is just a pure sine curve. That's called the carrier. The modulator is the actual signal that you're trying to encode into your radio signal. And there are a few different techniques. For AM radio, they modulate the amplitude. So they don't keep the amplitude of the carrier wave constant, but they vary it with the properties of the sound that you're trying to transmit. The signal that you're trying to transmit has been added to the carrier wave to produce a wave that looks like this. Your radio device will pick up that signal it will strip away the carrier wave and recreate the original signal that you're trying to listen to. The music, the voices, whatever you're sending. With FM, it's a little more complicated to understand, but what they're going to do is they're going to take whatever frequency you have for your modulator, and they're going to use that to modulate ever so slightly the frequency that they're transmitting. This will be greatly exaggerated compared to how it's going to work in real life, but it will give you a little bit of a visual on how it works. Again, when your radio picks up that signal, it strips away the carrier and goes back to the original sound that you're trying to recreate. So here's how it looks. Again, you're adding these two together to produce either an amplitude modulated wave or a frequency modulated wave. A newer technique would be to do neither of those and to encode your information digitally as a series of ones and zeros. With this, we can modulate either the amplitude or the frequency, but the nice part is you only need to have two different values. So one frequency could stand for a 1, and then a slight change in that frequency would indicate a 0. So as time goes by, your radio would pick up a series of 1s and 0s. It would then use some sort of algorithm to turn these back into the original information. I want you to realize, in addition to small-scale communication here on Earth with like radio and Wi-Fi and Bluetooth and things like that, we also use radio waves to study the heavens. One of the most famous examples of this was a scientist in the 1960s who was able to pick up radio signals from a faraway object, and what she saw was a constant repeating pattern of a radio signal that occurred over and over and over again. She correctly deduced it was coming from an object that had a strong radio signal, but it was spinning. So as it spun, we would pick up the signal, we'd lose it, we'd pick it up again. And based on the frequency at which we pick up the signal, we know the rate at which this thing is spinning. It turns out that these things are what are known today as pulsars. Okay, a very, very important discovery in the world of astronomy, thanks to radio telescopes and the ingenuity of our scientists. The second band is microwaves, and microwaves can also be used for communication, but they have one very special frequency among the entire microwave band that is very important for us because we use it for cooking. We have a magnetron that creates the wave of that specific frequency. We then have a thing that's going to deflect it all around the inside cavity of our microwave. And what's unique about that one specific frequency or one specific wavelength is that that frequency will not pass through water. Okay, most light goes right through water, but at that one frequency, the water absorbs that energy and turns it into heat. And it's not just water that does this. It turns out that that frequency can be absorbed by water, fats, and sugar. So some of the primary ingredients in some of the things that we cook. There's other materials where those waves will go right on through it and they won't generate heat. There's some materials like metals which will have really bad things happen when that frequency hits it. The metals will either reflect it and it'll be going all over your microwave, or they'll be generating voltages that cause sparks to jump between different parts of the metal. Again, we can still use microwaves for communication, and we can also use microwaves for the little fobs to enter into our car. So when we push that button, it could create a radio signal, but more often than not, it's high enough frequency that would be considered a microwave. One of the disadvantages to microwaves in terms of using them for communication is they are not going to be able to bounce off the ionosphere as well as radio waves, so they tend to be used for short-range communication. The final shorter, smaller frequency wave we want to look at is infrared light. And infrared is most often associated with trying to determine objects' temperatures. It turns out that most objects that are in the range of common objects around room temperature, body temperature, and even quite a bit above body temperature radiate most strongly in the infrared. So here's a picture of a person taken with visible light, and here's the same person doing the same thing, and this time the picture is taken with infrared. One of the interesting things about this is you could see that even though visual light does not pass through the dark trash bag, the infrared can pass right on through it. So different frequencies of light interact with matter differently. We saw it with the microwaves, and we could see it with the infrared. The other thing that's kind of neat is you can see that his glasses block the infrared, whereas glasses traditionally allow visible light to pass right on through. Here are some pictures I took myself. You can see the poor circulation I have in my fingers. And again, this is all thanks to my complaining during the winter or through infrared photography. Here's a picture of a kid who was petting a cat. The cat actually got up and moved, and the rug where the cat was laying still has an impression, a digital impression, a thermal impression I guess is best, a thermal impression of where the cat was, because it's a little warmer than the rest of the rug in the room. Here's another example showing that infrared cannot pass through glass. This is a coffee cup filled with hot water, and I'm going to put a piece of glass in front of the lens, and you'll see that the infrared is blocked, even though the visible light is able to go right through glass. We can see the same thing with a person. Hopefully you can see the pane of glass here. And you can see how the glass, even though it is transparent to regular light, is opaque in infrared. So anyway, I hope you have a little bit better understanding of infrared, microwaves, and radio waves. Again, these are frequencies of light that are lower than the visible light.